Stanford University.
Convolutional neural networks. There's actually a whole class, I think next quarter, on just convolutional neural networks for computer vision, where they've really changed the entire field. In NLP, they've had some impact, but not as much, which is why we don't have the entire lecture on just CNNs. But they are an interesting model family. They are parallelizable. They're very good on GPUs. And so we'll sort of look into them in detail today, understand hopefully by the end why they're so useful and fast to implement on GPUs, but really also give you at least some intuition. To be honest, there's much less intuition behind some of these very advanced CNN architectures compared to even some of the recurrent neural networks and LSTMs that we had. So we'll actually start today with a mini tutorial on Azure and GPUs. We want to encourage you all to really get started on that as soon as possible. Also, thanks everybody for filling out the survey. I think this one is one of the important sort of takeaway messages, which is overall, what do you think of the pace? And we're very happy to see that the majority are quite happy with the pace. It's kind of impossible with such a large class to not be too fast and not too slow for 100% of everybody, since people have vastly different backgrounds. Really sorry for the less than a third, I think, for whom it's too fast. I hope today will be not quite as fast, and hopefully in office hours and so on we can make up for some of that. So yeah, we'll talk about a couple of different CNN variants. We'll have a fun research highlight on character-aware neural language models. And then we'll actually also look a little bit into tips and tricks that are slightly more practical. And you'll observe that these practical details and tricks to actually making this particular CNN architecture work are super important. And without it, you really lose 10% or so of accuracy. Look a little critically at some of the evaluations that are going on in the field. And then we'll compare a couple of different models, which will lead us to a very new model called the quasi-recurrent neural network, which really just came out a couple of months ago. All right, with that, I'll do one organization slide before we go on to Azure. So project advice office hours, I would really encourage everybody who's doing a project to now come to project advice office hours every week. I've asked the groups that I'm mentoring personally to also, as a sort of a requirement, not all the groups were able to come every week. I encourage you all to come. I am keeping track of whether you're there. So also for everybody who basically is still undecided whether they should move on with their project, you'll see kind of where PA4 folks should be at in the next week or so. Really, you have to have run some baselines on your data set by now if you're doing your final project. If you don't even have your data set ready yet, you can't even run a simple, let's say, bag of vectors kind of baseline, it's starting to be really worrisome. So definitely make sure you start running your experiments, some simple things, baselines, could be just any logistic regression, you download some code somewhere, but you need to make sure you have your data set ready. Otherwise, it'll be too late. And for PA4 folks, we actually enforce that with a little additional deadline just to make sure you're really all going to be able to run it, because this is not one of those things that you can cram really hard and you work 10x and so you make 10x the progress, because your experiments will take a day to run. And so you run for one day, turns out at the end you had a bug, and then the deadline is there and you have nothing. So it happens every year, and we really want to make sure it doesn't happen this year, even though we're a bigger class. So we'll talk about that soon. Also, in terms of positive motivation, there's actually going to be a really awesome poster session that we're putting together. We have corporate sponsors that gave us some money. And they will allow us to basically give out prizes for you. We'll make it public, so hopefully a lot of folks will show up and check out your research. There's a lot of excitement, both from various companies, VCs. If you have an awesome poster, who knows, by the end you may have some funding for your startup. And we'll have food also. We'll have really nice catering, so it should be a really fun poster session. So hopefully you can be very excited about that in your projects. Yeah. Will there be enough food for everybody? It's a good question. We'll spend thousands and thousands of dollars on food. We hope there will be enough food for everybody. Shane is organizing it. He's nodding. Yes. Any other organizational questions around the poster, your projects? All right, then take it away on the GPU side. Nope, you're good.
All right, everyone. This is just intended to be a short public service announcement about basically how to get started with Azure and why you should get started with Azure in general. By now, every team should have received an email to at least one of your team members, probably to one of your Stanford emails. And you'll have this message, which is basically an invitation to join our CS324N subscription. And following the instructions of this email, you should sign up for basically GPU access. So far, like only 161 people have signed up, or teams have signed up out of the 311. And yeah, essentially, we want this number to increase because everyone should be using GPUs for reasons that we'll go over very shortly. And if you have any issues signing up, then please report the problems that you have to the Piazza Post 1830, which has the form also screenshotted there, and we'll help you essentially through any of the problems that you have with your subscriptions. Cool. So the more important question that we're going to go over is why should you really care about the GPUs? Well, first, yesterday we actually announced the milestone and for the final project and the homework. It's intended to be something very quick and easy, just a paragraph of what you've done, but we expect you to have used, like, at least experimented with running some code on a GPU by then. And this will be worth essentially 2% of your final grade, just if you do it or not. But really, down there, the better reason of why you should be using GPUs is GPUs will train your models much, much, much faster over much, much larger data sets. And specifically, Microsoft has offered us, I think, 311 MV6 instances on their Azure cloud. These use Tesla GPUs M60 if you're interested in the model. The specifications are, they have a huge number of CUDA cores, a huge amount of graphics memory, and they cost a huge amount of money each. You also get a nice CPU as well as a lot of system memory to go along with your instance. And the key takeaway here is that these are not your average like hardware that you have in your local machine. There's going to be way more power in terms of the CPU, in terms of the GPU, and in terms of, well, even for like the gaming, whatever hardware you have at home. And the speedups will be 10 to 20, maybe even 100, depending on the libraries that you're running. So in conclusion, please do get started on Azure as soon as possible. Fill out the form if you run into subscription issues. Come to office hours or file support tickets if you have technical problems such as not being able to spin up a VM, etc. And then also see our step-to-step guide to just get started with the process. For homework 4, the full assignment handout will go over essentially all the details, but decent models will take a long time to train. They'll take 1 hour plus per epoch, even on a strong GPU such as the previously described ones. If you don't do it with a GPU, you'll be spending a week, basically, just to train a baseline model. And then for the final project, if your project is sufficiently challenging that it needs, well, you have enough data or your problem is sufficiently challenging, you really do want to use a GPU if you want to receive a good score in this class. And that will be all. Cool.
Thanks, James. And by decent model, he also means decent implementations. So if your implementation isn't super well optimized, it will take you even longer. So again, not something you can cram on in the last couple of days of the class. All right. Any questions about Azure or Azure? What if we're not in the same group between homework 3 and 4? All right, so recurrent neural networks were pretty awesome and are pretty awesome, actually, and a lot of times the default model, but they have some issues. Namely, they can't really capture phrases in isolation. They can really only capture a phrase given its left side context. So what do we mean by this? If I want to have just a representation of my birth in this whole sentence, well, the recurrent neural network will always go from left to right, right? And so that phrase vector up there isn't going to just capture my birth. It will also capture the country of. And so sometimes when you have simple classification problems, you might actually just want to identify that there's a certain word or phrase in that overall document and just try to give that, the fact that that phrase exists in your overall document, to somewhere higher up in the final classifier that actually needs to classify this. But here, you will always go from left to right, or even if you have a bidirectional one, you go from right to left. But then you have the same problem, but on the other side. That namely, the intermediate, the words in the center of a longer document might get lost. You really have to keep track of them through every iteration. And of course, GRUs and LSTMs are better at doing that. They're better able to say, all right, don't turn on the forget gate, keep some things around, keep certain units on once you see something. But it requires a lot of the model to be able to do that perfectly. And so in many of the cases, you will see your classifiers only at the very end, once it's read the whole sentence. And that is another issue, because now, again, the gradient has to flow through this. And despite all the GRU and LSTM awesomeness, it's even hard for them to keep very complex kinds of relationships alive over many, many different time steps. So that's one issue with RNNs that CNNs are trying to resolve. Now, the main idea is, instead of computing a single representational vector at every time step that captures basically the context on the left so far, what if we could just compute a phrase vector for every single phrase that we have in a sentence? So if we have here the phrase, the country of my birth, we might compute in the very first step of these kinds of convolutional neural networks a vector for the country, just these two words in isolation, just country of my birth. So basically compute a vector for all the bigrams in the sentence, and then another one maybe for all the trigrams, the country of my birth, the country, and then for all the foregrams, the country of my birth. So hoping that if this was, for instance, sentiment classification, that one of these said not very good, for instance. And then if we capture that vector, and we kind of will try to eventually handle and push that vector all the way to softmax through some other forms that I'll describe soon. But that is basically the idea of the very first layer of a convolutional network for NLP. And this will, it will basically compute these phrase vectors regardless of whether that is a grammatical phrase. So we know from parsing, for instance, certain phrases like the country of is not really a proper noun phrase. It's sort of an odd ungrammatical chunk, but this model really doesn't care about linguistic or cognitive plausibility in any kind of way for language, right? So people don't read sentences that way, but you might be able to eventually compute several of these representations in parallel, and that's going to be a big advantage. So once we compute all these vectors, we'll group them after, but we'll get to that in a second. All right, so you might ask, what is convolution anyway? And so here is a very simple definition for any convolutional operator. So let's look at the simplest case of a 1D discrete convolution of a filter over another function at a specific point in time. You'll basically have a filter size here, capital M, and you'll basically multiply just a filter at different locations of this input. And so in computer vision, that will help us to extract very meaningful features, such as edges, from an image, and eventually more complex features. And for a 2D example, which you'll observe a lot in computer vision, we have this really great animation here from the Stanford Unsupervised Feature Learning and Deep Learning wiki page. So imagine you had an image that you see here in green, and that image, let's say it's only binary. And the first row of this image is 11100, and then the second row of pixels of this binary image is 01110, and so on. And you have a filter, and this filter here has numbers that you'll see in the small red font here. And I'll turn the animation off for a second so we can look at it without moving. Now, the filter here is basically 101010101. And now we're just going to, at every time step of the convolution, we're going to multiply the numbers of the filter with the numbers of the image. So we multiply, again, these red numbers from the filter with the images with the image values. And that will result, we'll basically multiply all of them, and then we sum them up. So very simple inner product if we were to vectorize these 3x3 blocks into a 9-dimensional vector, and we just have a simple inner product between those two vectors. Or we just multiply them here and then sum them up. So 1 times 1 plus 1 times 0 plus 1 times 1 and so on will sum to 4. And we'll basically move this filter 1 time step, 1 pixel at a time across the image. So let's look again. This looks like basically multiply all the numbers and then sum them up. And then we'll move 1 down and again move from left to right. Any questions? Yeah. That's a great question. What would be the equivalent of a pixel in NLP? And yes, you're exactly right. It will be a word vector. Before I jump there, are there any more questions about the general definition of convolution? Yeah. How do we decide on the convolution? So how do we decide what matrix it is? The matrix of the convolutional filter here, these red numbers, are actually going to be learned. So you have an input, and then you do backpropagation through a network. We'll get to eventually, it'll have the same kind of cross-entropy error that we have for all the other ones. It'll have a softmax, and we're going to basically backpropagate through this entire architecture, and then we'll actually update the weights here in this particular example in red. After they start with some random initialization, and then we'll update them and they change. And what's kind of interesting in computer vision, which I won't go into too many details in this class, but in computer vision, they learn eventually to detect certain edges in the first layer. In the second layer, they'll learn to detect certain combinations of edges like corners. In the third layer, they will learn to basically detect and have a very high activation, these guys here, very high activation when you see more complex patterns like stripes and things like that. And as you go higher up through convolutional networks and computer vision, you can actually very nicely visualize what's going on, and you'll identify, oh, like the fifth layer, some neurons actually fire when they see a combination of eyes and a nose and a mouth. Sadly, for NLP, we don't have any of that. It's one of the reasons they're not quite as popular in NLP. Yeah. Sure. So you have here M, your filter. So in the 1D case, that will just be, each, like F and G are just a single number. And now you're going to move over F. So imagine this was just 1 dimension. And so you move from -M to M. As in for the nth time step, you're going to multiply the filter, GM here, over this function input, and basically go 1 time step, and you sum up this product between the two numbers at each time step. Does that make sense? So you go from -M, which, if this is minus and this is minus, so you start, a little ahead of n, M time steps away, and then you keep multiplying the numbers until you have the whole sum, and then you have your convolution at that discrete time step n. That's right. M is your window size. And we'll go over the exact examples for NLP in much more detail. Yeah. How do we figure out the window size? We'll actually have a bunch of window sizes, so maybe it's a good segue to talk about the actual model that we'll use for NLP. So this is going to be the first and most simple variant of a convolutional network for NLP. You can really go to town, and towards the end, I'll show you some examples of how we can embellish this architecture a lot more. This one is based on a really seminal paper by Colbert and Weston from 2011. And then the very particular model and its various tuned details came from Kim from just 3 years ago. Basically, the paper title is A Convolutional Neural Network for Sentence Classification. All right, so as with every model out there, whenever you want to write down your equations, no worries, we're not going to go into a lot more derivatives today. Actually, no derivatives, because all the math is really similar to math we've done before. But it's really still important to identify very clearly your notation. So let's start. As the question was correctly asked, we'll actually start with word vectors. So we'll have at every time step I, we'll have a word vector xi. And that will be here for us now a k-dimensional vector. And then we will represent the entire sentence through a concatenation. So we'll use this plus and circle symbol for concatenating the vectors of all the words. And so we'll describe the entire sentence, which we'll have for our definition here, n many words, to be x from 1 to n. And that will be the concatenation of the first to the nth word vector. Yeah. Great question. Are word vectors concatenated lengthwise? Yes. For now, we'll assume they're all concatenated as a long row. All right, now we'll introduce this additional notation here, so we don't just go from 1 to n, but we might actually want to extract specific words in a range from time step I to time step I plus j, or in general, some other number of time steps. So if I have, for instance, x2 to 4, then I'll take the second, the third, and the fourth word vector, and I just have a long vector with just those 3 word vectors concatenated together. I'll let that sink in because it's all very simple, but we just need to make sure we keep track of the notation. So in general, our convolutional filter here will be a vector W of parameters that we're going to learn with our standard stochastic gradient descent type optimization methods. And we'll define this convolutional filter here in terms of its window size, and of course the word vector size. So h times k, so this is just a vector, it's not a matrix, there's no times in between the two. But let's say we want to have a convolutional filter that at each time step looks at 3 different word vectors and tries to combine them into a single number or some kind of feature representation. What we'll then do is basically have a 3 times number of dimensions of each word vector filter. So have a very simple example here. Let's say we have 2-dimensional word vectors. Of course, just for illustration, they usually be 50-dimensional or so. Let's say we have 2-dimensional word vectors, and we look at 3 different words in concatenation at each time step. We'll basically have a 6-dimensional W here. All right. So now, how do we actually compute anything, and why is it a neural network? Well, we'll have some nonlinearity here eventually. Okay, but before we get there, let's look at, again, we have our convolutional filter. Looks at h words at each time step. And again, note that W here is just a single vector, just as our word vectors are also concatenated into a single vector. And now, in order to compute a feature at 1 time step for this, what we're going to do is basically just have an inner product of this W vector of parameters times the ith time step plus our window size. So in this case here, we're going to, in the C1, for instance, we'll have W times x1 to 1, 2, 3. So we have here 3, so 1 plus 3 minus 1 goes to 3. So we'll basically just have the concatenation of those word vectors, inner product, simple sort of multiplication and sum of all the element-wise elements of these vectors. Then usually we'll have our standard bias term, and we'll add a nonlinearity at the end. Any questions about? That's a great question. So as you do this, the question is, don't the words in the middle appear more often? So here, I actually showed this example, and I have actually an animation, so you are jumping a little bit ahead. So what happens, for instance, at the very end here? And the answer will just be, we'll just have zeros there for the end. And we'll actually call this a narrow convolution, and you can also have wide convolutions, which we'll get to later. But yes, you're right. The center words will appear more often, but really the filters can adapt to that because you learn sort of how much you want to care about any particular input in the filter. Okay, so let's define this more carefully so we can think through the whole process. Yep. So the question is, rephrase it a little bit, what happens when we have different length sentences? And there will actually be, in 2 slides, a very clever answer to that, which is, at some point, we'll add a pooling operator, which will just look at the maximum value across everything. We'll get to that in a second. And it turns out the length of the sentence doesn't matter that much once we do some clever pooling. How's the size of the filtering affecting the learning? Actually, quite significantly. One, the longer your filter is, the more computation you have to do, and the longer context you can capture. So for instance, if you just had a 1D filter, it would just multiply a matrix with every word vector, and it actually you wouldn't gain much because it would just transform all the word vectors, and you may as well store transformed word vectors. As you go to longer filters, you will actually be able to capture more phrases, but now you're also more likely to overfit your model. So that will actually be, the size of your filter will be a hyperparameter, and there's some tricks, namely you have multiple filters with multiple lengths, which we'll get to in a second too, that will allow you to get rid of that. All right, so let's say again here, we have our sentence. Now we have all these possible windows of length h, starting at the first word vector, going to this, and so on. And now what that means is, since we do this computation here at every time step, we'll have basically what we call a feature map. And we'll capitalize this here as having a vector of lots of these different c values. And again, each c value was just taking that same w and having inner products with a bunch of the different windows at each time step. Now this C vector is going to be a pretty long n minus our window size plus 1 dimensional vector. And it's actually going to be of different length depending on how many words we have, which is a little odd, right? Because in the end, if we want to plug it into a softmax classifier, we would want to have a fixed dimensional vector. But intuitively here, we'll just, again, multiply each of these numbers on our W here with the concatenation, and we move along. Turns out we'll zero pad. And if you now think carefully, you actually realize, well, I kind of cheated because really that's what we should have done also on the left side. So on the left side, we'll actually also zero pad the sentence. So we do exactly the same in the beginning and the end of the sentence. All right, now because we have a variable length vector at this point, and we want to have eventually a fixed dimensional feature vector that represents that whole sentence, what we'll now do is introduce a new type of building block that we haven't really looked at that much before, namely a pooling operator or a pooling layer. And in particular, what we'll use here is a so-called max over time or a max pooling layer. And it's a very simple idea, namely that we're going to capture the most important activation. So as you have different elements, see here that you computed for every window, you have the hope that the inner product would be particularly large for that filter if it sees a certain kind of phrase, right? So namely, if you have, let's say your word vectors are relatively normalized, if you do an inner product, you'd want to have a very large cosine similarity between the filter and a certain pattern that you're looking for. And that one filter would only be good at picking up that pattern. So for instance, you might hope all your positive words are in one part of the vector space, and now you have a two-dimensional, a filter size of length 2 that looks at bigrams. And you want to ideally have that filter be very good and have a very large inner product with all the words that are positive. And that would then be captured by having one of these numbers be very large. And so what this intuitively allows you to do is as you move over it and you then in the end max pool, if you just have one word pair, one bigram, that it has a very large activation for that particular filter W, you will basically give that to your C hat here. And it can ignore all the rest of the sentence. It's just going to be able to pick out one particular bigram very, very accurately, or a type of bigram. And because word vectors cluster, and where similar kinds of words have similar kinds of meaning, you might hope that all the positive words will activate a similar kind of filter. Now, the problem with this is, of course, that is just a single number. Right? C hat is just the maximum number here of all the elements in this vector. So that would just be 5. So that could be one activation. If we used a ReLU nonlinearity here, this will just be a single number. So C hat is just that. Now, of course, we want to be able to do more than just find one particular type of bigram or trigram. We want to have many more features that we can extract. And that's why we're going to have multiple filters W. So instead of just convolving a single filter W, we'll convolve multiple of them. And as we train this model, eventually we hope that some of the W filters will fire and be very active and have very large inner products with particular types of bigrams or trigrams or even fourgrams. So it's also very useful to have some filters that only pick out bigrams, and you can actually get quite far with that. But then maybe you have some examples where you say, for sentiment, again, very simple example, it's not very good, or it was missing much originality, and now you want to have trigrams and filters of length k times 3. And so we can have multiple different window sizes, and at the end, each time we convolve that filter and we do all these inner products at each time step, we'll basically max pool to get a single number for that filter for that sentence. We have different filters of different lengths. How do we make sure they learn different features? Of same length or different lengths, yeah. Of same length, how do we make sure they learn different features? Well, they all start at different random initializations. So that helps to break up some symmetry. And then actually, we don't have to do anything in particular to make sure that happens. It actually just happens. So as we do SGD, from the random initializations, different filters will move and start to pick up different patterns in order to maximize our overall objective function, which we'll get to. It'll just be logistic regression. They will probably still learn different values, yeah. You update. So in the beginning, well, if they're exactly the same, you'll basically, as you pool, right, you will eventually pick, during backpropagation, the max value here. The max value will come eventually from a specific filter. And if they have the exact same, one, you would never do it. So, but two, if you did, they would have the exact same value. And then your computer will have to choose randomly one of the max, one to be the max. And if they're just the same, whatever, it'll pick one. And then it'll backpropagate through that particular filter. And then they're also going to be different in the next iteration of your optimization algorithm. Yeah? Is there a reason why we do the max that has high variability? So that seems like unstable. Is there a reason why we do the max? So in theory, nothing would prevent us from using min too. Though we, in many cases, use rectified linear units, which will be max 0x. And so max pooling makes a lot more sense because min will often just be 0. And so with ReLUs together, it makes the most sense to use the max pooling layer also. Could we use average pooling? It's actually not totally crazy. There are different papers that explore different pooling schemes. And there's no sort of beautiful mathematical reason of why one should work better. But intuitively, what you're trying to do here is you try to really just fire when you see a specific type of n-gram. And when you see that particular type of n-gram, because that filter fired very strongly for it, then you want to say, this happened. And you want to give that signal to the next higher layer. And so that is particularly easy if you choose a specific single value versus averaging, where you kind of conglomerate everything again, and the strong signal that you may get from one particular unigram or bigram or trigram might get washed out in the average. Great question. So once we have a bunch of different C hats from each of the filters, how do we combine them? And the answer will be we'll just concatenate all of them. We'll get to that in a second. So so the main idea is once you do max pooling, one of the values will be the maximum, and then all the other ones will basically have zero gradient because they don't change the layer above. And then you just flow your gradients through the maximum value that triggered that filter. So the question is, doesn't that make our initialization very important and lead to lots of downstream problems? And the answer is yes. So likewise, if you, for instance, initialize all your filter weights such that your rectified linear units all return 0, then you're not going to learn anything. So you have to initialize your weights such that in the beginning, most of your units are active and something will actually happen. And then the main trick or the reason why it doesn't hurt a ton to have these different random initializations, you have lots of filters. And each filter can start to pick up different kinds of signals during the optimization. But in general, yes, these models are highly non-convex, and if you initialize them incorrectly, they won't learn anything. But we have relatively stable initialization schemes at this point that just work in most cases. Great questions. All right, I like it. All right, so we basically now have, we're almost at the final model, but there's another idea here, and that combines what we've learned about word vectors, but extends it a little bit. Namely, instead of representing the sentence only as a single concatenation of all the word vectors, we'll actually start with 2 copies of that, and then we're going to backpropagate into one of these 2 channels, and not into the other. So why do we do this? Remember we had this lecture where I talked about the television and the telly, and as you backpropagate into word vectors, they start to move away from their glove or word-to-vec initialization. Right? So again, just quick recap, word vectors were really great. We can train them on a very large unsupervised corpus, so they capture semantic similarities. Now if you start backpropagating your specific task into the word vectors, they will start to move around when you see that word vector in your supervised classification problem and that data set. Now, what that means is as you push certain vectors that you see in your training data set somewhere else, the vectors that you don't see in your training data set stay where they are and now might get misclassified if they only appear in the test set. So by having these 2 channels, we'll basically try to have some of the goodness of really training the first copy of the word vectors to be really good on that task, but the second set of word vectors just stay where they are, have the good, nice general semantic similarities and vector space goodness that we have from large unsupervised word vectors. And in this case here, both of these channels are actually going to be added to each of the CIs before we max pool. So we will pool over both of those channels. Now, the final model, and this is the simplest one, I'll get to in a second, is basically just concatenating all these C hats. So remember, each C hat was one max pooled filter. And we have, in this case here, let's say M many filters. And so our final feature vector for that sentence has is just an R M dimensional vector where we have M many different filters that we convolved over the sentence. And then we'll just plug that z directly into softmax and train this with our standard logistic regression cross-entropy error. All right, we had a question? By having 2 copies of the word vectors, are we essentially doubling the size? Well, we're certainly doubling the memory requirements of that model. And we just kind of assume, yeah, you could think of it as doubling the size of word vectors. And then the important part is that only the second half of the word vectors you're going to backpropagate into for that task. That's right. We can use the same convolutional weights, but you can also use different convolutional weights. And then filter, and you can have multiple, and this model will have many of them actually, will have, that have 100 bigram filters, 100 trigram filters, and maybe 20 4-gram filters, and maybe even some unigram filters. So you can have a lot of different hyperparameters on these kinds of models. It'll quickly explode. For a given sentence, does the convolutional matrix stay the same? So this matrix here is the only matrix that we have. This is just our standard softmax matrix. And then before, we had these W filters, these vectors. And yes, each W is the same as you convolve it over all the windows of one sentence. All right, so lots of inner products for a bunch of concatenated word vectors, and then you max pool, find the largest value from all the n-grams, and that's a CNN layer and a pooling layer. All right, now here's a graphical description of that. Here, instead of sort of concatenating them, this just kind of simplified this. So imagine here you have n, same notation. We have n many words in that sentence, and each word has a k-dimensional feature vector or word vector associated with it. So these could be our glove or word-to-vec initializations. And now this particular model here shows us 2 applications of a bigram filter and 1 of a trigram filter. So here, this bigram filter looks at the concatenation of these 2 vectors and then max pools them into a single number. And as you go through this, you'll basically get lots of different applications. And you basically, for each of the filters, you'll get 1 long set of features, and then you'll get a single number after max pooling over all these activations from all these bigram positions. Yeah? So you see here, for instance, so the bigram filter is this channel, and then we'll basically max pool over that. And again, notice how here they use, indeed, the same filter on the second word vector channel, the one we might backpropagate into. But they will all basically end up in here. These are just, again, inner products plus bias and nonlinearity. And then we'll max pool all those numbers into a single number up there. And now a different, namely this guy up there, the trigram also convolves over that sentence and basically combines a bunch of different numbers here and then gets max pooled into a single number there. Great question. So do we always max pool over just a set of features that are all coming from the same filter? And the answer is, in this model we do, and that's the simplest model that actually works surprisingly well. but there are going to be, right after our quick research highlight, a lot of modifications and tweaks that we'll do. All right. There are no more questions. Let's do the research highlight, and then we'll get to how to tune that model. Should be on.
Hello?
Yeah.
Cool. So hi everyone, my name's Amani, and today I thought I would share with you a very interesting paper called Character-Aware Neural Language Models. So on a high level, as the title implies, the main goal of this paper is to come up with a powerful and robust language model that effectively utilizes subword information. So to frame this in a broader context, most prior neural language models do not really include the notion that words that are structurally very similar should have very similar representations in our model. Additionally, many prior neural language models suffered from a rare word problem, where the issue is that if we don't really see a word that often or at all in our data set, then it becomes really hard to come up with an accurate representation for that word. And this can be very problematic in languages that have like long tail frequency distributions or in domains where vocabulary is constantly changing. So to address some of these problems, the authors proposed the following model, where essentially we will read in our inputs at the character level, but then we will make our predictions still at the word level. So let's dive a little bit deeper into the model and see exactly what's happening here. So the first thing we do is that we take our input and we break it apart into a set of characters, where for each character we associate it with an embedding that we will learn during training. We then take a convolutional neural network and take its filters and convolve them over the embeddings to produce a feature map. And finally, we apply match pooling over time, which intuitively is selecting out the dominant n-grams or substrings that were detected by the filters. We then take the output of the convolutional neural network and pipe it into a highway network, which we're going to use to essentially model the interactions between various n-grams. And you can think of this layer as being very similar to an LSTM memory cell, where the idea is that we want to transform part of our input, but also keep around and memorize some of the original information. We then take the output of the highway network and pipe it into a single time step of an LSTM, which is being trained to produce the next word of a sequence given the current input. And the only thing different to note here is that we are using hierarchical softmax to make predictions due to the very large output vocabulary. So let's analyze some of the results. So as we can see here from the table on the right, the model is able to obtain comparable performance to state-of-the-art methods on the pin tree bank dataset while utilizing fewer parameters in the process. What's also really remarkable is that it is able to outperform its word level and morpheme level counterparts across a variety of other rich languages, such as Arabic, Russian, Chinese, Russian, and French, while using, again, fewer parameters in the process, because now we don't have to have an embedding for every single word in our vocabulary, but now only for every single character that we use. We can also look at some of the qualitative results to see what is it the model is exactly learning. So in this table, what we have done is that we have extracted the intermediate representations of words at various levels of the network and then computed their nearest neighbors. And what we find is that, like after applying the CNN, we are grouping together words with strong subword similarity. And then after applying the highway network, we are also now grouping together words that have strong semantic similarity. So now the word Richard is close to now other first names. We can also look and see how it handles noisy words. So in this case, the model is able to effectively handle the word look with a lot of O's in between, which it has never seen before, but it is now able to assign it to reasonable nearest neighbors. And on the plot on the right, what we see is that if we take the n-gram representations learned by the model and plot them with PCA, we see that it is able to isolate the ideas of suffixes, prefixes, and hyphenated words, which shows that at its core, the model really is learning something intuitive. So in conclusion, I want to sort of highlight a few key takeaway points. The first is that this paper shows that it is possible to use inputs other than word embeddings to obtain superlative performance on language modeling while using fewer parameters in the process. Second, it shows that it demonstrates the effectiveness of CNNs in the domain of language modeling and shows that, in this case, the CNNs in highway network are able to extract rich types of semantic and orthographic information from the character level inputs. And finally, what's most important is that this paper is combining the ideas of language modeling, CNNs, LSTMs, hierarchical softmax, embeddings, all into one model, which shows that basically we can treat the concepts that we've learned over the course of the quarter as building blocks and learn to compose them in very interesting ways to produce more powerful or more nuanced models. And that is a very useful insight to have as you approach some of your own projects, not only in the class, but also beyond. And with that, I'd like to conclude, and thank you for your attention.
Character models are awesome. Usually when you have a larger downstream task like question answering or machine translation, they can give you, 2 to 5% boost in accuracy. Sadly, when you run any kind of model over characters, think you have a, sentence or document with 500 words. Well, now you have a sequence of 500 times, maybe 5 or 10 characters. And I have a 5,000 dimensional time sequence. And so when you train your model with character levels, think extra hard about how long it will take you to run your experiments. So it's kind of a very clear sort of accuracy versus time trade-off in many cases. All right. So I mentioned this super simple model where we really just do a couple of inner products of a bunch of these filters, find the max, and then pipe all of that into the softmax. Now, that by itself doesn't work to get you to state-of-the-art performance. So there are a bunch of tricks that were employed by Kim in 2014. And I'm going to go through a couple of them since they apply to a lot of different kinds of models that you might want to try as well. The first one is one that I think we've already covered, Dropout, but we did, right? It's a really neat trick, and you can apply it in lots of different contexts, and it's actually differently applied for convolutional neural networks and recurrent neural networks. So it's good to look at another application here for this particular convolutional neural network. So just to recap, the idea was to essentially randomly mask or drop out or set to 0 some of the feature weights that you have in your final feature vector. In our case, that was Z. Remember, Z was just a concatenation of the max pooled filters. And another way of saying that is that we're going to create a mask vector R of basically random Bernoulli distributed variables with probability P set to 1, and probably 1 minus P set to 0. And so what this ends up doing is to essentially delete certain features at training time. So as you go through all your filters and you actually had a great bigram and another good bigram, it might accidentally or randomly delete one of the two bigrams. And what that essentially helps us to do is to have the final classifier not overfit to saying, oh, it's only positive, for instance, if I see these exact two bigrams together. Maybe it's also positive if I just see one of the bigrams. So another way of saying that is that it will prevent co-adaptation of these different kinds of features. And it's a very, very useful thing. Basically, every state-of-the-art model out there that you'll observe, hopefully somewhere in its experimental section, it will tell you how much it dropped out, the weights, and how exactly, what exactly the scheme of dropout was. Because you can drop out, for instance, for the recurrent neural network, you can drop out the same set of features at every time step or different sets of features at every time step, and it all makes a big difference, actually. So this is a great paper by Jeff Hinton and a bunch of collaborators from 2012. Now, if you carefully think through what happens here, well, at training time, we're basically, let's say it's 0.5, probability P is 0.5, so half of all the features are randomly getting deleted at training time. Well, then the model is going to get used to seeing a much smaller in norm feature vector Z, or Hadamard product here, R times Z. And so basically, at test time, when there's no dropout, of course, at test time, we don't want to delete any features. We want to use all the information that we have from the sentence. Our feature vector Z are going to be too large. And so what we'll do is, in this case here, we'll actually scale the final vector by the Bernoulli probability P. So our WS here, the softmax weights, are just going to be multiplied and essentially halved. And that way, we'll end up in the same order of magnitude as we did at training time. Any questions about dropout? What's the intuition? So some people liken dropout to ensembling models. And intuitively here, you could have, let's say, deterministically, you were dropping out half of all your like the first half of all your filters, and you only train one model on the first half of the filters, and you train a second model on the second half of the filters, and then in the end, you average the two. That's kind of similar, but in a very noisy variant of what you end up doing with dropout. And so in many cases, this can give you like 2 to 4% improved accuracy. And when we look at the numbers, you'll notice that it's those 2 to 4% that gets you that paper published and people looking at your method. Whereas if it's 4% below, it's getting closer and closer to a very simple bag of words model with discrete counts. Is it possible to drop out the link instead of the node? So you could actually drop out some of the weight features as well. And yes, there is actually another variant of dropout. There's the filter weight dropout, and there is the activation dropout. So in this case here, we'd have activation dropout. And they have different advantages and disadvantages. And there's, I think it's fair to say that, especially for NLP, the jury is still out of like which one should you always use. I think the default you just filter out, and the original dropout is just to set to 0 randomly the activations and not the filters, not the filter weights. All right, now, one last question. So basically, this will have a certain norm. And at training time, the norm of this is essentially, say, halved if you have a probability of p to multiply the features with 0. And so what that means is that overall, this matrix vector product will have a certain size and a certain certainty also once you apply the softmax. And if you don't want to basically be overly confident in anything, you want to scale your W, because at test time, you will not drop out anything. You'll have the full z vector, not half of all the values of the z vector. And so at test time, you want to use as much information as you can get from z. And because of that, you now have a larger norm for z. And hence, you're going to scale back W so that the multiplication of the two ends up in roughly the same place. Very good question. So what's the softmax here? So basically, z was our vector for some kind of sentence. And I use the example of sentiment because that is one of the many tasks that you could do with this. So generally, sentence classification or document classification are the sort of most common tasks that you would use this model for. We'll go over a bunch of examples in 3 slides or so, a bunch of data sets. Awesome. So now there's one last regularization trick that this paper by Kim used in 2014. It's actually not one that I've seen anywhere else. And so I don't think we'll have to spend too much time on it. But they essentially also constrain the L2 norm of the weight vectors of each of the classes. So you have here, remember this is our softmax weight matrix W, and C dot was the row for the Cth class. And they basically have this additional scheme here where whenever the norm of one of the rows for one of these classes is above a certain threshold S, which is another hyperparameter they'll select, they will rescale it to be exactly S. So basically, they'll force the model to never be too certain and have very large weights for any particular class. Now, it's a little weird because in general, we have L2 regularization on all the parameters anyway. But they saw a minor improvement. It's actually the only paper that I can remember in recent years that does that. So I wouldn't overfit too much on trying that. Now, it's important to step back and think carefully. I described this model, and we described it very carefully. But when you think about it, you now have a lot of different kinds of tweaks and hyperparameters. And you have to be very conscious in all your projects and every application in industry and research and everywhere of what your hyperparameters really are and which ones actually matter to your final performance, how much they matter. In an ideal world, you'll actually run an ablation where maybe you have these 2 word vectors, the ones you backprop into and the ones you don't backprop into. How much does that actually help? Sadly, in very few examples, people actually properly ablate and properly show you all the experiments they ran. And so let's go over the options and the final hyperparameters that Kim chose for this particular convolutional neural network model. And they basically tried, this was, the one amazing thing is they actually had the same set of hyperparameters for a lot of the different experiments. A lot of these are sentiment analysis, subjectivity classification. It's really most of the experiments here. But they had the same set of hyperparameters, which is not very common. Sometimes you also say, all right, here are all my options. And now for every one of my data sets, I will run cross-validation over all the potential hyperparameters, which if you think about it is exponential. So it would be too many. So then the right thing to often do is actually set boundaries for all your hyperparameters and then randomly just sample in between those boundaries. So for instance, let's say you might have 100 potential feature maps for each filter, for each window size. Now you say, all right, maybe I'll have between 20 and 200. And you just say, for each of my cross-validation experiments, I will randomly subsample a number between 20 and 200. And then I'll run experiments with this number of filters on my development split, and I'll see how well I do. And you say I have maybe 100 experiments of this kind. You'll quickly notice that, again, why do you need to start your projects early? Because your performance will also depend highly on your hyperparameters. And if you don't have time to cross-validate, you may lose out on some of the accuracy. And especially as you get closer to potentially state-of-the-art results, which I think some of the groups will, that last couple % that you can tweak and squeeze out of your model with proper hyperparameter search can make the difference between having a paper submission or having a lot of people be very excited about your model or ignoring it, sadly. Yeah. Great question. Do you do that sampling for one hyperparameter at a time or not? In the end, in the limit, it doesn't matter which scheme you use. But in practice, you set the ranges for all your hyperparameters, and then you sample all of them for each of your runs. And it's very, very counterintuitive that would work better than even a grid search, where you say, all right, I'm going to, instead of having 100 feature maps and randomly sample between 20 and 200, I'm going to say I'm going to try it for 20, 50, 75, 100, 150, or 200, or something like that. And then I just multiply all these 6 or so options with all the other options that I have. It quickly blows up to a very, very large number, right? Let's say each of these, you try 5 different options. That's 5 to the number of many hyperparameters that you have, which if you have 10 hyperparameters or so, it's 5 to 10. It's impossible to run a proper grid search on all these hyperparameters. And so it turns out computationally and through a variety of different experiments, I think the paper is by Yoshua Bengio and some of his students a couple of years ago, that random hyperparameter search works surprisingly well and sometimes even better than a relatively fine grid search. Until you run out of money on your GPU, or until the paper deadline comes around or the class project deadline comes around. Yeah, in the perfect setting, you have the final model that you think has all the ingredients that you would want, and then you can let it run until you run out of resources, either time or money or GPU time, or you annoy all your co-PhD students, which I did a couple of years ago at Stanford. Fortunately, we learned at some point to have preemptible jobs so that I could use the entire cluster, but then when somebody else wants to use a machine, it will just put my job onto into the cache or onto memory, or even save it to disk, and anybody else can sort of come in. But yeah, ideally, you'll run with all the computational resources you have. And of course, this is depending on how much you care about that last bit of accuracy. For some of the papers, it can really matter. For some applications, if you work in medicine and you try to classify breast cancer or something really serious, of course you want to squeeze out as much performance as you possibly can and use as many computational resources to run more hyperparameters. So there are actually some people who tried various interesting Bayesian models of Gaussian processes to try to identify the overall function in the hyperparameter space. So you basically run a meta-optimization where instead of optimizing over the actual parameters W of your model, you run an optimization over the hyperparameters of those models. You can do that. It turns out the jury is sort of out. But a lot of people now say just do a random hyperparameter search. It's very surprising, but that is, I think, what the current type hypothesis is for being the best way to do it. Yeah. Oh, you can't. So the question is, how do we make sure the same set of hyperparameters end up with the same results? They never do. And some people, we could talk a lot about this. It's kind of fun. And it's like the secret sauce in some ways of deep learning. But some people also say, I'm going to run the same model with the same hyperparameters 5 times. And I'm going to average and ensemble those 5 models because they all end up in a different local optimum. And that ensembling can also often help. So at the end of every project that you ran, if you have 100 models that you've trained, you could always take the top 5 models that you've had over the course of your project and ensemble that, and you'll probably squeeze out another 1 or 2%. But again, probably don't have to go that far for your class projects. It's only if it really matters in your downstream application, medical applications or whatever, to need to do that. And in many cases, what you'll observe is in papers and competitions, people write, this is my best single model, and this is my best ensembled model. And then in the best ensemble model, you can claim state of the art, and your best single model might be sometimes also the best single model, but sometimes you also have a more diverse set of models. All right, last question about ensembling and crazy model hyperparameters.
Should we take something away from the fact that ensembling still works? Doesn't that mean that maybe we need a larger model?
Great question. Why does ensembling still work? And shouldn't we just have a better single model? You're totally right. There are various ML researchers who say, I don't like ensembling at all. We should just work harder on better single models. And Dropout is actually one such idea that you can do. There are other optimization ideas that try to incorporate that. Yeah, you're right. In some ways, what that means is we still don't have the perfect optimization algorithms that properly explore the energy landscape of our various models. All right, so let's go over the extra hyperparameters that they used here. So basically, we want to find all these hyperparameters on the def set. Super important. You get minus 10% if I see you run on the final test set all your hyperparameter optimization, because that means you're now overfitting to your final test set. One of the number 101 machine learning rules, never run all your hyperparameter cross-validation on your final test set. That's the one thing you want to run maybe once or twice. You can ruin your entire career if you do that and you publish it. It's never worth it. Don't do it. All right. So on the development set, on your development test set, or sometimes called def set, Kim here tried various different nonlinearities, and in the end chose the rectified linear units. It's actually very common, and nowadays you almost don't have to run and try that. You just use ReLU as the default. He had trigrams, 4 grams, and 5 grams. For the various filter sizes. Somewhat surprising, no bigrams. It surprised me. He had 100 different feature maps for each of these sizes. So 100 trigram filters, 100 4-gram filters, and 100 5-gram filters. So the more you have, the more likely each of them can capture different kinds of things. So if you have, for instance, just a simple sentiment classifier, you can have 100 shots at trying to capture various types of negation, for instance. Here. Then Dropout, just simple in the middle. Half of the time, all the features are set to 0. He chose, for this funky regularization trick, s equals 3. Somewhat surprisingly, your mini batch size will often also change your performance significantly. So if you don't usually want to have gigantic mini batch sizes for most NLP models. So here he had a mini batch size of 50 during mini batch SGD training. And he used the word-to-vec vectors, pre-trained on a large corpus, and he had 300 dimensional word vectors. So that was a lot of hyperparameter search you can think that was going on in the background here. Yeah? Wouldn't a higher mini batch size guarantee that we have less noise while training? The answer is yes, but you actually want the noise. You have a very non-convex objective function here, and what Dropout does in SGD is to actually introduce noise so that you're more likely to explore the energy landscape instead of just being very certain about being stuck in one of the many local optima that you have. So a lot of optimization tricks and training tricks of neural networks in the last couple of years can sort of be described as adding noise into the optimization process. And now this one here is also super important. During training, how do you select your best model? So one option is you just let it run, and at the very end, you take that last output. But what you'll often observe is a pattern like this. Let's say you start training. So these are your iterations. And this might be your accuracy or your F1 score or your RU score, your BLEU score, or whatever you're using for your model. And now you'll often observe something like this. and as you train over time. And now, if you take just the very last one, maybe here, maybe that wasn't as good as this random spot that as it did stochastic gradient descent, it found just a randomly really good spot on your def set. And so what Kim does, and what actually a lot of people do, is during training, you keep checking the performance here. And again, this is your development accuracy. And then you pick the one with the highest accuracy, and you set those weights to be the weights for that particular experiment. And another side trick, just because they're fun, you can also sample multiple times and then ensemble those weights or average those weights, and that sometimes also works better. All right, still some black magic. All right, so that was a lot of good details for how you tune your models. So here are now some of the results. So here we basically have only, sadly, in this whole paper, 4 ablations and 4 of the options that are really carefully outlined, and all the other hyperparameters we don't know how important they were or the variance of them. Yeah. You can do both. So you can average the weights, which is very counterintuitive, but also often works. If you average the predictions, now you have to keep around, let's say you have an ensemble of the 4 top models, you have to keep around your model size times 4, which is very slow and not that great. So it's less commonly done, especially not in practice. Oh, sorry, can I define ablation? So an ablation study is essentially a study where you start with your fancy new model that you described in all its details, and then you say, how much did each of the components actually matter to my final accuracy that I describe in my abstract? So let's say we have a cool deep learning model with 5-layer LSTMs and some attention mechanisms and some other clever ways of reversing the input in machine translation, for instance, and so on. And now you say, all right, this model got me, a root score of 30 or 25. Now, as a practitioner, when I read that paper, and even as a researcher, I want to know, well, you mentioned 5 tricks. Which of the 5 were actually the ones that got you to 25? Was it, yeah, you want to know because you might not want to use that entire model, but you want to use that one trick. So in this case here, for instance, he has this regularization trick, and he has the dropout. How much did the dropout actually help versus this trick? Which one should I now use in my downstream task? In this paper here, and I don't want to single him out, this is really, sadly, very common in the field. Nobody tells you, nobody gives you a nice plot for every single hyperparameter that says, for this hyperparameter, let's say dropout p, between 0 and 1, this was my accuracy. Yeah, so the ablation would say, I will take out one particular modeling decision. So let's say in this case, for instance, the ablation here is, do we need the multi-channel, 2 word vectors, one you backprop into, one you don't? Or do we only have a static channel, as in we keep, he called static here, just keeping the word vectors fixed in the beginning, versus having only a single channel where we backpropagate into the word vectors, versus having both of the word vector sets. And this is the ablation that he does here, the ablation over should we have 2 sets of word vectors or not. And as you can see here, well, it actually, sometimes it buys you, 0.7 and here 0.9 or so, but sometimes it also hurts. So here having the 2 channels actually hurt by 0.4. And these are actually relatively small data sets, all of them, so the variance is actually relatively high. The simplest one is you actually just have random word vectors, and you backpropagate into them, and you just learn the word vectors as part of your task. So no pre-training of word vectors whatsoever. That's actually fine if you have a gigantic training data set. So if you do machine translation on 5 gigabytes of, don't do it for your project. I hope we discouraged everybody from trying that. But if you do machine translation on a very, very large corpus, it turns out you can just have random word vectors, and you have so much data on that task that as you backpropagate into them and update them with SGD, they will become very good as well. That is totally right. So Arun here correctly points out, and I mentioned this, like these are actually very small data sets. And so there's very little statistical significance between most of these results here. I'm maybe SST 0.9. I forgot all the various thresholds of statistical significance for the various papers. I think this one might be significant, but certainly like MPQA, for instance, is a very small data set, so this 0.1 difference is not statistically significant. Great question. So the question is, as you do this, let's say you had your full data set. You say, this is my training data. This is my development split, and this is my final test split. And we had properly randomized them in some way. Now, if I choose, based on my development split and this development accuracy here, this model, then this model was only trained on this, and only in sort of some meta kind of way used that def split. Now, what you could also do, and what you should always do if you have an actual convex problem, which sadly we don't have in this class very much, what you would do is you find your best hyperparameter setting, and then you actually retrain with that whole thing all the way until convergence, which if you have a convex problem is great. You know you have a global optimum, and you probably have a better global optimum because you used your entire training data set. Now, it turns out in many cases, because there can be a lot of variance in your training for these very non-convex neural network models, it helps a little bit to just ignore that that def part of your data set and just use it to only choose the highest point. It's largely because it's a non-convex problem. Great question. All right. We have 4 more minutes. So one of the problems with this comparison here was actually that the Dropout, for instance, gave a 2 to 4% accuracy improvement. And overall, and you'll see this in a lot of deep learning papers, they'll make claims about this is the better model. Sadly, when you look at it, there's some models here that they're comparing to that came out after or before Dropout was invented. So we can be very certain that some models from pre-2014 didn't use any of the kinds of tricks like Dropout, and hence the comparison is actually kind of flawed. And sadly, you'll observe this in most papers. Almost very, very few people in the community will go rerun with the newest and fanciest optimization tricks like Dropout or Atom and better optimizers and so on, and re-implement all the baseline models of previous authors, and then have a proper comparison, run the same amount of cross-validation on the second best model and other people's models, and then have a really proper scientific study to say this is the actual better model versus this model came out later, had the benefit of a lot of optimization tricks, and hence came out on top. So you'll see that a lot, and it's in some ways understandable because it takes a long time to reproduce 10 other people's results and then start tuning them. But you have to take a lot of these with a grain of salt because the optimization, as we see here, makes a big difference. So 2 to 4%. When you look at even some of my old papers, like 4% is the difference between whether this model is the better one or not. Still, it is kind of a very cool architecture, this convolutional neural network. The fact that it can do so well overall is something that is quite remarkable. It's relatively simple. And the nice thing is, with these filters, each of the filters is essentially independent, right? We run max pooling over each of the filters independently. So each filter can be run on one core of your GPU. And so despite having 300 different filters, you can run all of those 300 in parallel, max pool in parallel, and then you have very quickly you can compute that one feature vector and pipe it into the softmax. So that is actually a huge advantage of these kinds of models. Now, we don't have that much time left, so I'm not going to go into too many details, but you can really go to town and put together lots of convolutions on top of pooling layers in a variety of different ways. We spend a lot of time trying to gain intuitions of why this LSTM gate has this effect. I don't think we have a good chance of going here into the third CNN layer and having some intuition of why it's this kind of layer versus another. They're really they really get quite unwieldy. You can have various kinds of convolution. So those are in some sense also hyperparameters. You can ignore basically zero pad the outsides, or you can just not run anything that would require an outside multiplication and only run convolutions when you have for the insides. Basically, this is the narrow versus the wide convolution. You can eventually run the convolution also not over the time steps, but in later layers over the feature maps. So there are a lot of different options, and at some point, there's no more intuition of why you should do this in the third layer of these text CNNs. One of the most exciting applications was actually to take such a CNN, have various pooling operations, and in the end, take that as input to a recurrent neural network for machine translation. So this was one of the first deep learning machine translation models from 2013 that actually combined these fast parallelizable CNNs with a recurrent neural network to do the machine translation that we've seen. So we've essentially described this model entirely in the lecture before, but now we're replacing the encoder part. Instead of having an LSTM here, we have a CNN here, and we give that as input to all the time steps at the decoder part of the model. Very cool model. Now, probably I'll end on this slide, and we'll maybe talk about this quasi-recurrent neural network that combines the best of both recurrent and convolutional models for another lecture. But basically, you now know some of the most important and most widely used models for deep learning for NLP. We have the bag of vectors. Surprisingly, works quite well. When you combine it with a couple of ReLU layers, it can actually even, in some benchmarks, beat this convolutional neural network that we just described. So very good baseline to run for a variety of different projects that we're discussing. We discussed the window model already, where we have basically a very clean model to classify words in their contexts. Now we know the convolutional neural networks, and we had a lot of variants of recurrent neural networks. So hopefully you have most of the tools. On Thursday, Chris will talk about recursive neural networks or tree-structured recursive neural networks that will be much more grammatically and linguistically plausible, but also have some downsides. All right, thank you.